What you know is this has for parallel, so the bond of the C11, but here for the mix so. First of all, thank you for giving me the opportunity to speak here. I see that most of the audience is that physics more in hard material, so I try to prepare a talk that would be maybe a bit more descriptive than we normally do to make sure that at least the ideas or the things that we're interested in come across, and also the methodology and what we want to do. So our lab is working on soft materials, mostly the chemistry, not biology. We're definitely working on that matter, but chemistry, physics, and mechanics. And we're trying to really cover several scales. So today I'm going to talk about fracture. So maybe our view of what fracture is from different scales. Let me slide change. Yes. So first of all, soft materials, just a short definition. We both work with classical applications like tires, seals, and also with companies. And also we're interested in developing new materials with chemistry. And those are some examples that have come up. Soft robotics, for example, the Harvard group is very active in that type of work. Also, elastomeric actuators. Elastomers are very deformable. They can be used for artificial muscles, so there's been development in that area to use electric field for that. Flexible electronics to interface conventional electronics with body. And why are we interested really in specifically fracture? And the main reason is really that you would like two things from many of these materials. First of all, often you want reversible deformation. So you really would like to have something that can undergo a number of cycles. We want elasticity. It's not a fluid, it's really a solid. And also, fracture is really what limits the usage. So this is just a picture of a motorcycle tire, maybe from somewhere in Taiwan, a scooter tire. And the usage range, and mostly for practical reasons, dimensions are controlled by fracture resistance. So if we could improve and get better materials, improve fracture resistance, you can make lighter structures in general. This also applies to soft materials. This is why companies are interested in this, apart from, again, the fundamental science. Now, what's the physics of fracture? Just in one slide, for those who really have never seen this. So if you take a material, fracture mechanics people like to put defect. So the idea is materials break by propagation of defects. So you actually put an initial crack in here, and you define this as an energy balance. So this G here is a strain energy release rate. You're deriving the energy relative to the crack length, and you do an energy balance for this crack to advance. And you have two criteria that are actually equivalent for linear elastic material. One is that of a local stress, so it's given by the stress intensity factor K, and it varies in function of distance from the crack. So when the stress gets too high, you break bonds, you break chemical bonds, and the material breaks. And you also have an energy criteria. When you have enough strain energy around the crack, then the stresses are high too, and the crack propagates. Now, for linear elastic material, these two critical values are connected. So essentially, energy or stress criterion gives you the same result. And there is a separation of the length scale. So basically, the crack is very local, and the strain energy comes from a reservoir, which is far away. So this is the really classic picture of what's called linear elastic fracture mechanics. It works really well for things like glasses. So this is an AFM picture for slow propagation of a crack into an inorganic mass. And there, this is an AFM, so this is 2 microns inside. So you're looking at something that's maybe 10 nanometer in diameter. So a piece of glass will break by very, very localized bond fracture. This is a hard plastic, PMMA, another hard plastic used in glues. And in this case, this type of picture of separating the scale between strain energy coming from far away and bond breakage localized works pretty well. We understand, I would say, this type of problem from the mechanical point of view relatively well. Now, in soft materials, it's more complicated. So this is actually a piece of rubber. You're going to see a little movie. Crack propagates from right to left. Okay, here's one thing. Now, here you can see that things are moving, the crack is actually moving. If you look at, this is supposed to be a tip of the crack, you can see it's blunted, and you can see there's a lot of deformation here. Of course, chemical bonds have to break, because this is a solid material. So inside here, you have a network of bonds, but it breaks in a very delocalized way. So there's a lot of collective effect that causes these bonds to break. This is another example of soft material. This is a glue. So this is like a piece of Post-it. It's put into an electron microscope, and this is a surface of a plastic, of a hard plastic. It's being pulled away from it, and here we're going. It's more a picture of debonding. So you're looking at, this is actually our solid material. It's just very deformable. And it does stick, but actually the adhesive forces in here are van der Waals only. Yes? It looks more like a, it's absolutely, it's a crack, it's a surface. Well, it's a question of radius. Basically, if you're thinking of the previous glass, the radius is a few nanometer. This is going to be typically hundreds of microns. So there is no essential difference, but the radius is very different. And so the locus of bond fracture will be much larger. The main difference is that in the glass, the radius is similar to the molecular scale. So somehow you can look at the problem as a molecular problem, and you're still localized there. Here, clearly, it's not possible. So, but otherwise, indeed, it's a surface. So if we're looking at the length scaling here, and this answers to part of this, we have a macroscopic scale, which is the sample size, where you have your crack. Then, if you look at this crack tip, but it's really indeed fairly rounded, you have an intermediate scale, 10 to 100 micron, generally for these soft materials. This is really where polymer physics is important, where you have damage mechanisms like cavitation, formation of filaments, as you could see from there, and molecular friction, which is important. Then if you magnify again, you will get the molecular scale, because these materials are actually polymer networks, so they're soft, flexible chains that are connected with cross-linking points. So we would like to understand how breaking this, and this is really just a cartoon, affects this, and then eventually the microscopic scale. So it's a hard problem. It's a really, even though it's nothing like the complexity of living things, but still for this type of material, it's not easy to understand it. One soft problem that we're going to look at is to say, okay, for tough material, it's been really speculated that sacrificial bonds, and shown to a certain extent, are important, which means that you design inside the material some chemical bonds that are weaker than the others or that break before the others. And this breakage in two steps is something that actually makes the material harder to break. So there's a number of examples here. This is double covalent networks. This has been really developed by a Japanese group in Hokkaido. This is a hydrogel example where you have a covalent network and an alginate ionic network interpenetrated. This is from the Harvard group, Jiang School. And this is from we also had one example here with nanocomposite systems. In all cases, you have really internal bonds that break before the actual microscopic material completely fails and propagates the crack. So we're going to really look at this one in more detail because in a way it's a simpler system. It's elastic. The other two have significant time-dependent behavior, which makes them more complicated. But this is still an elastic material, and it's due to it's really a molecular composite. So here is a little cartoon of how we make these materials. So we're also chemists, so we make our own material. So you start by synthesizing what I would call the filler network. So you just make a polymer network by incorporating reactives and cross-linkers. So you're making something that looks like a mesh. Of course, these are all fluctuating random chains. We're above the glass transition, so it's molecules connected. It turns out that this type of network can be swollen by solvent, but also by monomer. So you can actually use a building block of the polymer to swell this material. And in the next step, we do this by UV polymerization, but you could do it by other means. You can transform this monomer part into a polymer. So you're making actually a polymer inside this first network here. This blue one gets, in this way, stretched. In the last step, you evaporate the solvent, so you have a little bit of shrinkage, and your final little piece of material here is larger than the initial one here by the factor lambda 0 in all three directions. So you have isotropic stretching. The blue chains are being stretched because they cannot really move apart, while the red chains are just random chains, they're random coil in the statistical mechanics sense. Now, important parameter in these kind of materials where you can really change the design is the volume fraction of the blue chains in there and also the pre-stretch. So if the two are connected because of filling the volume, and this pre-stretch here is 1 over the volume fraction to the third power. Now, what the Japanese group discovered in 2003 is that if you make this volume fraction very low of the blue chains, so 3 to 15%, then you make a composite that actually has much better mechanical properties. So initially they really stumbled on that a little bit by luck. They were not really looking for it. And then there were a number of papers that really tried to explain why that is. It turned out to be a really powerful concept to generalize toughening material. So most of the material is this unstretched or lightly stretched matrix network in a way, and this is the filler network. The way it works is that if you compare, this is this initial network, you would think, if you're a polymer chemist, that if you can stretch it all the way to the point where these chains forming the mesh, they have an average length. When they're fully stretched, you get to the maximum extensibility of your material. So if you look at the single molecule, it does this. Initially you have entropic elasticity, then you have enthalpic, and you actually get to strain hardening and breakage. So in principle, it should do that, but in reality, this material will break at a much lower extension for crack propagation. If you do a swelling, so now your material is pre-stretched, so you're using up some of the stretching, and now the maximum extensibility of this material here should be less than this one. So in principle, it should reduce your maximum extensibility when you go from this to this from the molecular standpoint, because these chains are not pre-stretched, these ones are. Now, is that true in reality? I mean, if you actually make these materials and you test them mechanically, you stretch them, this is what you get. So this is the initial network down here. So this is stress versus stretch. So this is larger than 1. This is the initial material. This means three times the initial length. So this is lambda 0 equal 1. So this is the non-pre-stretch. As you pre-stretch to 1.5, 2.2, and 2.3, you can see that the stress at break goes up quite a lot. So the material gets much tougher. And if you look at the extensibility, it doesn't change very much. So this is actually exactly what you have in your tires. I mean, the rubber that is used in the tire is filled with nanoparticles. They do exactly this. If you have nanoparticles, the extensibility doesn't change, but the stress increases. Now, how can we understand this? If we try to renormalize things by the first network stretch, so you see these materials are all made from the same initial sample, this one. So you start from this, and you do swelling at different level of swelling. Now, let's renormalize the data by our lambda, the experimental one, times the pre-stretch. So now these 4 curves fall into something that looks like a master curve. Here it is different, the stress is different. But what I would like to point out is that now this is really the stretch of the initial network that we're plotting here. And it actually breaks much sooner for the sample that we made initially. And as we embed the sample into a matrix, the stretching increases more and more. So this is exactly the opposite of what we would have predicted in a way from the molecular standpoint. If you pre-stretch, you will break sooner. But here you can see that the network is actually breaking later and later. It's being protected by that matrix network. This is an intriguing result that actually is much more general than this model system. So to understand this a little bit better, we use tools that have been developed by chemists now in maybe 2010, 2012, which have some connection with biology tools. And we use mechanochemistry to actually do something in terms of visualization. So this is an example of Steve Craig at Duke. So the idea is to incorporate some molecules into your network that when they break, would create an active group that can, for example, become fluorescent, can emit light, can react. So you're using mechanics to actually trigger the reaction. You apply a force, And then once you get the reaction, that reaction will have some effect on your material. So we're going to use here three types of mechanochemistry molecule. One is this one, it's a dioxetane, it's a luminescent molecule, so it emits some photon with a fixed probability when you actually break it, so then we can detect that photon. So this really detects bond breakage. Then we are going to use this one, spiroperan. This is the first one that was developed by a group of Nancy Sotos and Scott White here at University of Illinois. So this is a cycle opening. This is a reversible one, which opens up at a certain force. And finally, this anthracene, I'll show you an example. This is more for confocal imaging. If you break this particular molecule here, you end up with a fluorescent fragment. So the material becomes fluorescent if you have bond breakage inside the material. So the idea is to use this molecule as marker, as label into our material. So I'm going to show you what you can learn from this. So to synthesize the polymer, this is the work of my talented student Yinju Chen. So you can incorporate here this particular molecule and or either one of these three as a crosslinker. So you actually, when you make your first network, you introduce all the ingredients in this mold, and instead of using this blue crosslinker, which is the standard one, you put some, it's typically of the order of 0.1% that you introduce. So it really doesn't really change the properties of your material, which is something we can check. But you introduce a certain number of these bonds that are mechanically active. Now, this spiroperan has been tested also in single molecule experiments. So this is a great work by Steve Craig, again at Duke, and he made a polymer with many of these groups in series, and then looked at the AFM force displacement curve and saw that there was a plateau around 250 piconewtons. So the cycle opens at 250 piconewtons. What's interesting here is that there is a change in absorption of light when you go from spiroperan to myrocyanine. So spiroperan doesn't really absorb in the visible, so you have a transparent material, but myrocyanine does absorb, and the material becomes, in our case, blue. So this is something that we can actually use to detect an average force. So this is a movie of one of these materials being tested. You can see it's transparent as it's being stretched, but now look at the color change. It does become blue, and when it breaks, it also becomes purple. So this is something that we can use, but I'm not going to talk about the purple, but just about the blue as you stretch it. So what you get is this. So you indeed, as you stretch your material, you change the absorption. It spatially varies, even though, so if you want to actually use quantitatively this data, there's a bit of averaging to do, and you have to actually take the ratio of the different colors. Sorry for this. So you can actually see here the blue component, the green, and the red. The interesting thing is that even though this spectrometer would be better to actually get the total spectrum, this is something you can do with a simple RGB camera. So with a cheap camera, you can actually get a pixel by pixel information about the RGB. So here what you see is the color change, and then you see in yellow the actual stress. So the measure of the stress can be after a certain threshold, because you have no signal below this point, so no signal about 1.5 megapascal in this case, but this strain hardening material gives you a definite direct signal of the stress. It turns out that, of course, what you're detecting is a concentration of activated molecule. The molecules are distributed randomly, this is statistical, but the average concentration of activated molecule depends on the stress. So what can you do with it? I mean, one of the things you can do is mapping. So here we're looking at two different materials made with different properties, different fracture energies, and this is a stress strain curve with notch sample. So the sample has an initial crack, it's being stretched. If it was a linear elastic material, this would be really not very interesting because we can predict everything with a simulation. But for these materials that are nonlinear, it's not quite as easy. And here I'm going to show you two imaging at two different points. So one that is the more strain hardening here, this is the actual, this is color coded, this is 4 and this is 2 MPa. And you can see directly the stress distribution. So this is not that easy to do. I mean, there's a number of techniques that give you the strain, and by, for example, digital image correlation, particle tracking, But to get directly the stress, you have to have a stress probe inside the material. So this is actually direct pixel by pixel measurement, where you can see where the high stresses are above and below the crack. Usually people see these images in undeformed configuration and it looks spherically symmetric. This is the actual deformed one where you're stretching. You can see that these two materials, this one is actually tougher, but the stresses are much lower than in this one. So actually far from the crack they're lower, but still it's much more resistant. So this is one information that we can get. Another thing that we can get is from the stress, we can get the strain energy. We could get it from the strain, but for strain hardening material, it's actually more accurate to get it from the stress. And here we can see that if we actually measure the strain energy, these two materials actually do break at fairly similar level of strain energy close to the crack. I told you before that we can also detect bond breakage. This is maybe more interesting and more original. And here I'm going to show you an example related to fracture. So this is stress strain of a material. These are loading, unloading curves. And you can see that there's actually no residual deformation. So this is an elastic material that shows some sort of plateau, some yielding. And the reason of this yielding, which is not really a yielding in the plastic sense, is that you have a very strong softening. So I'm going to show you again a little movie. And in this movie, if you look up here, you'll see that there is a necking. Yeah, there is a necking process here. And the material splits into two zones, a highly stretched zone. Now it's completely highly stretched. And in the end, it will break. So we're in this regime here. This is loading and unloading, while this is continuous loading. But it looks like there is a kind of softening, a very strong softening. That was very peculiar, because normally you don't see this in elastic, really not in elastomer. And Gonscrew speculated that this was due to sacrificial bond breakage inside, and that you had these blue, they also use blue for the hard material. The blue domains were actually breaking up into pieces. So their picture was that before this yielding process, one of the two networks was intact, and then after the yielding, it was broken in different pieces. So we were examining this hypothesis. So the idea there is to introduce the luminescent molecule, so the signal is not very high, but it does directly detect in real time bond breakage, so you can do it during the experiment. And here again, a little movie. I hope that there is enough contrast, but then I have, so here, you don't see very much. I think the sample should be seen over here, but I think I'm going to go directly to the images here. So actually, during this test here, we're looking at strain and this yielding. You've observed the sample, and you see actually initially homogeneous light emission above this point here, number 2, that shows us that we are breaking bonds inside the material, but randomly, and not in a localized way. As soon as we get here to this point, we start breaking non-randomly, and we have localization of bonds at the point where you go from the less stretched to the highly stretched. And we can actually quantify that. We see here a localization, then it moves, and we see the necking exactly as in the real-time experiment. So we can actually quantify the breakage. So this tells us that indeed there is one breakage, so it looks consistent with the hypothesis, but that's not really enough. A better way to actually, an additional way to look at it is to measure the stress before and after we have this damage. So in this case, this is the network. We can introduce our marker molecule in the blue network or in the red. We can also put it in the matrix to see how the stress is transferred from the filler network to the matrix network. So this is what Yinjun did. So he introduced spirogram, the stress detection molecule, in the filler network and in the matrix network. If the hypothesis of breakup into different pieces is true, then this network here should be unloaded at the yield point. So we made different networks with the same macroscopic elastic material. They all had yielding, but they contained the label in different places in the material. So now let's look at the result. Now, if we put the label in the first network, we see the necking, everything stays quite blue. If you look at the color here, there is no unloading. Actually, unloading would be characterized by a change of color to purple, as I was showing you in the fracture machine. We don't see any purple, so there is necking, but there's no unloading of this first network. On the other hand, if we put the spirogram in the second network, we see, I hope you can see, the blue color in the neck bar. So in the unnecked bar, there's no blue, but as soon as you break, there is blue. So that means that that particular region is now under stress. So both networks are carrying the load. So this is not really the initial hypothesis. The initial hypothesis was that the second network was carrying all the load. So you were going from the stiff to the soft. You transfer from one to the other. In reality, you transfer from the stiff, unbroken, and the soft to something that is a mixture. And this mixture really depends on the initial design. So it's a bit more complicated. You can't just mix soft and hard together and just have a linear combination of the two. The final result really depends on how you break. So right now we are really looking in more detail how this particular blue network is broken, what triggers it, and how do you go from random bond breakage to correlated bond breakage. So how is this now relevant for fracture itself? Because this is just linear extension. So if I look at fracture, what we want to know is really where are we breaking bonds in front of the crack, because this is what really causes it to move. And one of the hypotheses is that these sacrificial bonds actually slow down crack propagation, and so that tough material would have more broken bonds in front of the crack tip. So that we could prove by introducing these bonds in the filler network. And now here we're going to see a crack propagation. It's recolored, so everything you see corresponds to light emission. If it's not blue, the crack is moving from right to left. So I hope I can stop it. I'll play it again and then stop it. So that, okay. Move it. Okay. So here, the crack actually sits here. The experiment has to be done completely in the dark. And all of this region here, which is millimeter, it's 1 or 2 millimeter, is actually quite intense light emission, which is due to this bond breakage. Now, this is one particular material, which indeed is quite tough. If we do the same experiment for 3 different materials, this initial one in red was the initial network. The breakage is not detectable. So that means it's such a small scale that we cannot even detect the light emission. Of course, the sample does break, but we cannot detect it. Now, if we get to the double here, this is a slightly pre-stretched network. It actually sees spring stiffening, but at breakage point, there is actually some bond breakage. We don't see any bond breakage in uniaxial extension for this material, but at the crack tip we do. So this is an important also point of fracture, is that you may not see any damage in your material when you stretch it, but when you actually break it, you always have some damage in front. And this is this tougher one here that has very large energy dissipation, indeed has a very large volume here of dissipation. So with this particular experiment, we could really prove how this bond breakage was directly instrumental for toughness. Now, another point is, can we still detect the yielding at the front of the crack tip? I saw before that indeed we can detect bond breakage, random bond breakage. We don't know where it is, but we identified in the previous experiment that there was some kind of yielding, but in uniaxial extension. What of a material that doesn't yield in uniaxial extension, but could it yield at the crack tip? So we tried to do the experiment with the mechanophore in the second network. So it needs to be activated to see anything. And we put it at the crack tip, and unfortunately, we didn't see anything. So there was no color change in front of the crack tip. So we were wondering, okay, is that because the region is too small? At this magnification, we can't see it. Or maybe it's not activated at all, and our hypothesis is wrong. So what we did is we actually took advantage of another property of spirophran. It also gets fluorescent. So when you change from spirophran here to myrcene, this particular molecule has an emission in fluorescence, so around 620 nanometers. So it's possible to make observation with a microscope, a fluorescent microscope. So then, of course, we were wondering, particularly my student, whether you would actually see something in this case. And it turns out that you do. So here, this is a low strain. The crack tip is hard to see, it's yellow here, but critical strain means just before the crack propagates. And here you can see the yellow dot here, which means that there is a little bit of yielding in the material in front of the crack. As it propagates, it becomes quite larger. There was a question about the surface. It's a very blunted crack. So this is really interesting. Why? Because the material itself does not show any yielding. So this is the actual stress strain curve if you do just a uniaxial test of your sample with no notch. So there is actually no defect in here. And it breaks right here. There's no yielding. But as you propagate the crack, you have this yielding. So what it tells us is in most of these tough materials, breakage occurs in two steps. You first break some stiff phase, and then you break the soft phase. And the transition between the two and what controls it is very much a collective effect, where we just start now to understand a little bit better how it works. So I'd like to finish the talk just with sort of future things. This is all unpublished work. So we can also use a molecule that becomes fluorescent. It turns out that this molecule here with anthracene is a really interesting one to use. And as it breaks, it stays permanently fluorescent with very low photobleaching. So this is very much what biologists do. We introduce fluorescent molecule, and then we can use confocal microscopy. It's not used really in materials very much. It's really used more for living and for cells. So it turns out that this particular molecule can be excited at 400 nanometers. So 400 nanometer, you have a laser in most confocal microscope, and it emits around 500. It takes a week to synthesize. This is the sort of weak spot of it. Maybe later it will be easier to make this kind of molecule, but right now we have to do it ourselves in the lab. So we put this into a confocal macroscope. So instead of using a microscope where it's typically in inverted configuration, we use a low magnification confocal setup, which was actually developed for biologists who wanted to look at fetus and larger objects. But we can also use a crack, so we can put a tensile device underneath the confocal microscope and then illuminate it and do a 3D image of the crack tip. Of course, there are some issues: absorption, calibration. You have to correct for aberration if you want to get quantitative values of intensity. So it's a bit different than imaging. Usually biologists are interested in imaging. Here we're interested in measuring. So that causes few more complications, but it's not unsurmountable with proper calibration. It's possible to actually be quantitative. So I'm going to show you here an image of what we can see. So this is now a 3D image of a crack, and here the light intensity, it's asymmetric because the intensity depends on depth, but you're actually looking at the damage at the crack tip. So you can see that it's very much a 3D process. And you could guess that from the first image where we're showing you these fibrils. But right now, we really are studying precisely this 3D process to see how this material can break at the molecular level and then go from the molecular level to the more microscopic level and connect that with fracture energy. So with that, I would like to thank you for your attention. I'll be happy to answer any questions on the details that are missing in this presentation. Thank you very much. Well, there's a lot of unknown. I think this question of, well, there's two things. One is how to design better materials is not something that we understand all that well. There's a lot of, I would say, rule of thumb that people in companies know very well, but in terms of physical model, even approximate physical model that could actually describe this in a predictive way. Say, okay, if you do this with your chemistry, you're going to get this property. We don't have it yet. So that's definitely completely open at the moment. So I presented advances. I certainly didn't say that the problem was solved, otherwise I would be out of a job. So But really, I think there are a number of issues about breaching length scales, which are not known either from the modeling side and from the experimental side. Now, I don't know controversy about the theory of brittle fracture. Even brittle fracture has controversy as well, because it's never completely brittle, for one thing. We still, even if the scale of the, let's say, plasticity is very small, that doesn't mean we understand it at that scale. So even at the nanometer, tenth of nanometer length scale, the issue of whether it's going to be brittle or ductile, whether things are going to plastically deform or actually break bonds, is not easy to simulate, even for brittle materials. I'm certainly more interested in ductile, in the soft material. One of the reasons is the optical length scale. I mean, the soft materials deform at scales that are optically accessible. So that means you can do real-time experiments, because doing real-time experiment of fracture on harder materials is tricky, because you have to do it in an electron microscope, then you're actually damaging your material as you observe it, while optically we don't have that issue. So for sure, this is a little bit like, in that sense, easy to do the observation. On the other hand, the hard thing with soft materials is that they cannot be frozen. So you cannot really easily, because they relax. So you have to really do an experiment in real time. Otherwise, it's very hard to, or post-mortem completely. Once it's broken, you can look at it. But to actually stop the propagation and make observation, like they do for brittle material, it's not really possible. It wouldn't be representative.
Okay, yeah. So in the ICAM spirit of crazy out-of-the-box questions, there's been a lot of work recently in two-dimensional materials on origami structures. You know what those are? So can I actually think of those as one material which is solid and one material which has nothing in it? Is that any useful connection here?
Well, there is, I mean, I think the key difference is that here we do have, it's a bit like having a origami structure and putting another material around it. Imagine, I mean, I think the good analogy is that it's more like a composite. When you're making a traditional composite, you have fibers and you put them in different arrangements that you know are going to be mechanically sound. And then you cast, let's say, an epoxy resin around it, or you do that with a rubber if you want to, and you're making a composite. Here, we do make a composite of that type, but at the molecular scale. And it would be nice to be able to design. Where the field is very open is that the internal structure, we are using a pretty simple network, really just a rubbery network. You could use all kinds of things and swell them with a matrix. The physics that's interesting there is that if you just have your network structure, which could be a origami or it could be any structure you want, if it breaks, whenever you break something, the force that's no longer there has to be redistributed. That redistribution process is crucial to the soundness of the whole structure. So if you put a matrix around it, the matrix picks up some of the load. And how it picks up the load is really the essence of this particular problem, and there is a connection. So it's really the composite idea.
I'm interested in this connecting and breaking that you showed, the movie
Yes.
of this long strip. So there was an area that was necking at the top and the rest was not strained, and then instead of breaking, it became strained at the bottom with an area not strained in between.
Yes.
Is this something that's predictable, where this area of non-strained material, or is that associated with the defect, or it seems very much interesting.
Okay, so the nucleation of the necked area is certainly related to defects because it's random. I mean, if you make 3 different samples, the nucleation point will be at different points. In the particular video I showed, there was even 2 nucleation points. But we are at a level where the stress is almost, the nominal stress or the force stays about the same. So you actually have a nucleation point because there is a little bit of time dependence. They are essentially elastic material. I mean, they don't have much. If I do the experiment faster or slower, there is very little difference in terms of mechanical response. On the other hand, once it's nucleated, the propagation is really due to the fact that you have two stable states. You have an undeformed state and a highly deformed state where you have string hardening. These two states coexist, and so and in between, it's not stable. So you really jump from one to the other. This is the classic necking process that you also have in metals, you have it in thermoplastic, in polyethylene, your garbage bag will do that, but it's not elastic. The difference is that in your garbage bag, it will not return once it's oriented.
So when you go back down again.
When you go back down, the really unique feature there is that when you go back down, you have almost no residual deformation. So you can stretch everything to 600%, and then it goes back down, even though it's internally broken. So it's a very specific structure, which you have that in your tire. Not exactly that, but something similar.
Okay. Thank you very much.